As I make a mess of this right now, we have this publication, and basically within this publication, we are advocating a particular kind of classroom model, and probably it's reasonably familiar to you because I've talked about it to some extent on the shows that we've done until now. Now, one of the things we like to sort of help people with is that to make a transition to this classroom it's quite I mean, for many of us, probably for all of us to some degree, it's quite a transition away from what we do on a regular basis. So we thought long and hard about how we could support that process and how we could resource that process. I mean, the biomechanics course and resources are an example of that. However, we'd like to look in on a bit more of a personal level, I suppose, at how we can support you. And as a result of that, we've launched this the EverLearner Pioneers program. And you're very welcome to come here, mypexam.org, the EverLearner Pioneers. And we'd really like you to come and have a read of this blog post, which expresses why we're doing this. And, there's a bit to read here, and I encourage you to do that. But what we kind of like you to realise is that what we're going to ask the pioneers, and we have 12 people in this program so far, what we're going to ask the pioneers to do are these items here. So working towards the model, reporting back to us half-termly, sharing any research they do with us, participating in online conversations, of which we got our first one this Wednesday with Heather Lane, and so on. And we're going to provide colleagues with, obviously support, future resources. We're also going to kind of provide them the logo that they can use on any of their publications or social media, and also we're going to provide sort of discounted fees for various things as well. So financially, hopefully, it's relevant, and you sort of achieve this by getting in touch with Mike, and you can see the contact details here. Okay, so that's that. And one thing I just wanted to emphasize for you is that we have a really vibrant Facebook page for this process. So even if you think about it on this level, if you're interested in moving in that self-paced learning model that we've been discussing, and I personally have been advocating, then we can support you a substantial amount through this stream of sharing and information that members of this group are sharing. So think about, you might try this method out, you might come up against a barrier or a stumbling block or teething problems or whatever, and people in this group are going to help you to solve that. And I cannot emphasize enough the professionalism of those involved with this right now, and the thoroughness and the supportiveness of the people that have been involved with it so far. I mean, it's absolutely fantastic and great to see. A lot of conversations taking place here, and I would really encourage you to consider signing up to this program and getting involved. If you're going towards that self-paced learning model, we want to hear from you. Mike, that's Mike Pryor, mike@mypexam.org, and we'll see if we can get you involved. Okay, let's get on with the show.
Okay, let me turn the sound off on the delay there because we had that going. Welcome, one and all. Thanks for being here. It's really appreciated. Our fourth session of 6, so we're kind of getting there, right? Look, we've got a really busy session, so we're going to get pretty much straight on with it. We've got Marta with us this evening. I don't know if you're going to appear on the screen. You're actually here this week, Marta. So well done for making your way back from Barcelona this time.
Thank you. Hello. Hi.
And Marta's going to be, let's call it, filling in for Anna last week. So Marta's with us this week. We're trying to distract ourselves a little bit from what is a tumultuous political day in Marta's homeland of Catalonia. So we're trying to not think about that too much, and we'll get on with this. So a couple of things for me before we do start. First of all, just to repeat what we said in that little kind of advert-y bit, we've got this TEL, the EverLearners Pioneers program. If you are doing anything with self-paced learning in your classroom and you think you might benefit from being part of that group, it's not something we're trying to profit from or anything like that. We're just trying to share the conversation and enrich conversation. If you're doing that, anything like that, and you're interested in being part of it, then come along, get in touch with us, and we'll get you involved. We've actually got a live show tomorrow at 6 o'clock all about that. We'll be publicising it everywhere, so you won't be able to miss it. So that's the first thing. Secondly, as always, please do subscribe to the YouTube channel and add a thumbs up. It really does help us if you do that for us to be able to do more of these things. So we'd appreciate that. And finally, just make sure you've got with you notes pages, that you've got with you. You're going to need a ruler, for example, within the session. So ideally, you're going to have a ruler as well. And you need pencil and maybe a couple of different coloured pens. If you could sort of grab hold of that kind of material, that would be really useful for this session. So all that being said, we're going to make a start straight away. So Marta, if you could switch us over onto the Canvas stream, please, that would be really useful, and we will make a start.
Okay, so let's move on and let's actually get on with this. So, I mean, for me, this topic we're going to look at today, I think in some ways it is almost like a quintessential feature of biomechanics, or let's say it's a quintessential feature of that notion of studying A-level biomechanics. It's one of those classic things that students are going to either grasp or they're not going to grasp it. And for me, again, if we think about it from the teacher's perspective for a second, of course, it makes sense that the colleague planning and prepping lessons on this understands this and can demonstrate this and grasp these concepts. But perhaps even more than that, what we want to kind of achieve with colleagues is that teachers have a deep understanding of why this structure and this process works. So that's at least what I'm going to try and achieve today. Let's see if we actually get to that point. So anyway, we're going to look at projectile motion, and we touched on it last session when we looked at the shot put example 1, which I'm broadly going to repeat here. But let's move things on. Let's get on with it. So, look, you guys already know about how we model our classroom, and this is what we'd call, in some broad sense, our stock lesson. Our stock lesson is self-paced. Our stock lesson is self-directed by the students, and we run that lesson like that. We run lessons like that about 6 lessons out of 10. Now, I'm going to mention a particular variation of this classroom structure that I tried with this specific content. So, with this specific idea of projectile motion, I tried this model and it worked. This was in a period of time before this model kind of existed. So this model wasn't in place at this point. But at that point, I already had video content. I already had paper-based resources. I already had some games and activities. It's just that the big difference was that in the lesson I'm describing to you now, which is kind of some hybrid between what I used to do and what I do now, is that we all went at the same pace. Okay? And I don't mean that we went at the same pace through the class, because of course some students would be here, some students would be here, some students would be here, and so on. But we went through the same pace for the course. So that was to say that we would have a lesson on, in this case, projectile motion. So we'd have varied resources, and we'd all do those in different orders and at different rhythms to suit the individual learner. But the course broadly moved at the same pace. So that is how, that's, if you like, the difference. And the way I set it up was that it was kind of like this. We had the lessons available online and the quizzes. We had the worksheets, some of which I'm going to show you now. We had the activity sheets, some of which I'm going to show you now. But over here, this was a different kind of process. This was a demo space. Okay, so the way I did it here is that at certain times, imagine you've got a kind of a clock on the wall. At certain times, we had an agreement that, I don't know, I don't remember what time of day it was, but at 3 p.m., say, let me just change colour, at 3 p.m., say, in this class, that I was going to do a demo on this table of how to vector illustrate, say, a shuttlecock, for argument's sake. Okay. And the way that worked is that if the students at 3 o'clock felt that they needed that extra support, they would come over to this space and watch the demonstration. But this is very important about the demonstration. It was non-auditory. So the demonstration was non-auditory. Now, that's not a rule, it's just how I did it, you understand. So what I basically did here was that students came over here, and I didn't actually do it on the board. I just used a sort of a large piece of paper, and I demonstrated here how, one of the skills that I'm going to show you in a few moments' time, which is how to look at, how to analyze projectiles, okay? So on that basis, it was kind of really, it was a really versatile class, because students had their teaching, students had their exercises, students had their little kind of practice things and stimuli to make them learn it better, and they had visual demonstration of one of the core skills. So on that basis, I personally think that was like a really useful lesson, because they still had their past papers, they still had their mark schemes, they still had their worksheets, but the students had teaching, they had me there in that sort of computer tutorial sense, a bit like you'll get now, but they also had me in terms of like a specialist demonstration. I'm not saying I'm the best at it or anything, but I guess I knew what I was doing and demonstrated it for them in that way, and students could then go back and take that skill, or if they didn't need it, they didn't take part in that. Okay, so it's just something I wanted to share with you. So let's take projectile motion, and let's remind ourselves at broadly what we looked at in the last session. We basically said last time around we basically said that this shot, if released, let's say it's released at this point here, this shot, if released at this point here, is going to travel, and it's going to, not sure how parabolically I've illustrated that, it's going to land somewhere down here. And the idea of that curve, even though I've drawn it rather scatterly, in fact, I'm going let me redo it. I'm not happy with it. This curve should be symmetrical. Okay, so this curve, that's a little bit better. This curve should be symmetrical to some degree. Now, the only other thing I'd say about this at this particular point is notice where the release height is. Notice the release height and notice the landing height. Okay, landing height. Notice the release height and notice the landing height. So obviously in this example, we can say that the release height is here. There's our, let me just change color. There's our release point. There's our release height. So it's at whatever that height is. And here's our landing height. So what can we say here? We can say here that release, that was not what I meant to write, that release in terms of height here is greater than landing. Okay, is greater than landing. Okay, so if we've got release height being greater than landing, this has a particular impact for the flight path. So one of the things I'd encourage you to think about is that if the release height is above the landing height, then generally speaking, what we're going to find is that the optimal angle of release is going to be, that's meant to be less than, this thing here, less than 45 degrees. And you can kind of see that shallow flight here. So let me confirm, if the release height is greater than the landing height, okay, such as, you know, throwing a javelin or a shot or something like that, then we're saying that the angle of release should be less than 45 degrees. Secondly, if we had a different example where, let's say the release equaled the landing height, so the release and the landing height were the same. I mean, I'll ask you guys, what do you think the optimal angle of release would be? Okay, so have a little think about it, post it in chat if you feel like, and while you're thinking about that, I want to put our third option really. Our release is actually lower than our landing. What would our optimal angle of release be? Okay, and what would we come up with as answers for that? But I'm going to encourage you guys to realize that if the release height and the landing height are the same, then the optimal angle of the release is going to be in or at approximately 45 degrees. If the release height is lower than the landing height, then we're going to get an optimal angle. Of greater than 45 degrees. So the only thing I would ask you to think about, additionally to that, is what would be examples of this. Well, we've already got an example of the release being higher than the landing. Our throwing is an example, okay, assuming it's not a cricket throw, which is, you know, being caught at roughly the release height. What about release height being equal to landing height? Well, this would be something along the lines of a long jump. Okay, so a good example would be a long jump, okay, for release and landing height being the same because they're at the same level. But what about release height being below? So in release height being below, we've got the release height here, and the object is landing like this. What would an example of that be? And we have an example from golf. We have something like a raised green, you know, the green area being above where the tee shot, say, or the fairway shot is being played from. But we have another example as well of that last one, and that is the idea that we have something like a high jump, okay? Because if you think about a high jump, okay, by its nature, they're going to jump at greater than 45 degrees because they're trying to jump for height. But the other thing about the high jump is they're landing on a mat. Okay, so I've exaggerated it here with my flight, but they're taking off from the floor and landing on the mat. Okay, so it's a bit exaggerated, but you can see how the angle of release would be steeper as a result of that. Our long jump is our classic example of release and landing being the same, and something like a shot or a javelin is our classic example of our release height being above our landing height. So I encourage you to think about that. But where do we really want to go with this? Well, this is where we bring our ruler into play. Okay, so I've got my ruler. I can remember how to use this thing. I've got my ruler over here. And the first thing I'm going to do, in fact, let me get rid of that for a second. The first thing I'm going to do about the flight path of my shot is I'm going to identify on it where the center of mass is. So obviously with a uniform object like a shot, we already know that its center of mass is in the middle of the object. Now what we're going to do is we're going to apply all vectors that we can to that object. So first things first, we're going to take our ruler, and this is a relatively heavy object, so I'm going to create something like that. I'll get rid of the ruler. I'm going to create a weight vector down. So there's my weight vector like that. And it's relatively long because the object is heavy. And one of the things I'd encourage you guys to realize and to work with your students is no matter where we put this shot in this flight, that weight would be equally big. The weight is consistent. The mass and the effect of gravity, acceleration because of the effect of gravity, is equal no matter where it is in the flight. So regardless of where we start in the flight, that weight is going to be equal. And the most important thing is that weight is significant. This is a heavy object, so the weight has to be big. Is it as big as sort of a human being? No, it's not as big. What's an Olympic shot for men? I think it's like 7 kilos, something like that. So it's a heavy object. Now, we also want to apply the other force acting. And the other force acting, or the only other force acting, is air resistance. So first things first, let us address what causes air resistance to be greater. So air resistance greater if, and what are the ifs? Why would air resistance be greater for us? It's greater if the object is moving fast. Better language there would be of a high velocity. Okay, so moving fast. Air resistance is greater if we've got a greater frontal cross-sectional area. So if the object is really broad, such as a human torso, for example, okay, so greater frontal cross-sectional area. So the greater this front is, the greater the air resistance is going to be. And finally, we've got what we call surface characteristics. If the object is kind of rough, characteristics, if the object is rough and kind of catches the air, then the air resistance is greater. So the rougher the surface, think about like a shuttlecock, for example, has bumps and glue all over a feather shuttlecock, then of course those surface characteristics are going to catch the air at high speeds. But let me be absolutely clear, this one is by far the most significant. So what causes an object to have high air resistance is if the object is moving very fast. Okay, so let's now apply that to our shot put. How fast is this thing actually moving? And of course the answer to that is, well, James, it's moving pretty slowly. This guy's putted the shot, and it's going to be in flight for something like 1.5 seconds to 2 seconds, and it's not going very far. Okay, so we're talking about something like 10 meters per second, something like that, for this object to be moving, not a particularly fast speed. So on that basis, what we can do here, let me just make sure I've got my angles right. What we can do here is we can apply an air resistance, and our air resistance is always going to be applied back along the flight of the object. But our air resistance, let me keep that sort of consistent colour. Our air resistance is only going to be, let me just see what I've done there. I'm going to change colour. Our air resistance is only going to be something like that. I'm going to change to yellow so it's slightly clearer. Our air resistance is only going to be something like that because the object is moving not fast but slow. And then what we're going to do is we're going to make that into a vector, and we're going to label it. And we're always going to remember that whenever we're doing an illustration, we must have our direction of movement arrow, so we must include that as well. So the question for me now is then, how do we get a resultant force for this object? How can we, previously when we've looked at our learning, we've said, right, if we've got that plus that, it equals 0 net force. Or if we've got that plus a big up arrow, it equals a small up arrow. Well, how do we get these are what we call the resultant forces. How do we get the resultant forces here? And of course the answer to that is what we looked at last time, is we use a parallelogram. Okay, so we use a parallelogram. So let me bring that into play. So what I'm going to do now, and you will literally measure this. You will literally measure this and encourage your students to measure this too. A lot of noise in the background there, apologies. I'm going to do a little dotted line like that. So that dotted line is parallel to this air resistance vector. Can you see that parallelness to the air resistance vector? Now what I'm going to do is I'm going to turn my ruler back to 90%. I think I missed there. And now what I'm going to do is I'm not sure I've quite got that straight. Now what I'm going to do is I'm going to use my green like this. And now what I've got, and hopefully you can see it from what we did previously, now what I've got is a parallelogram. Now I think I've messed mine up slightly here, but what we can do here is that our resultant force, remember it's resultant force, which I'll do in a pinky color. So resultant force, okay, always has to start from the origin. And in this case, this is the center of mass of the object. Okay, so our resultant force is also going to start from the center of mass. But this time, the resultant force is going to move to the adjacent corner. Okay, the adjacent corner. Now, if anyone's interested, before I get into that, let me draw that in first of all. So what we're going to do here is we're going to take our parallelogram, use our ruler, line it up really neatly like this, not quite there, like that. And now what I'm going to do is I've got a resultant force like this. Okay, so now I have my resultant force. Okay, my resultant force, which of course in this case is closer to the weight force, the weight vector, because the weight vector is greater, it's dominant. Now, a couple of things. If you think back to your, depending on how old you are, your GCSE or your O-level mathematics that we all did, you might remember studying trigonometry. You might remember studying Pythagoras' theorem, for example, which basically said the sum of the the square of the hypotenuse is equal to the sum of the squares of the other two sides. So why am I mentioning that now? Well, the important thing to realize is, and I'm going to remove this line straight away. Please don't draw this on your illustration. It's just to show you the model. Is that if we take our two vectors, our air resistance and our weight, if we were to produce the hypotenuse of that, if that was a right angle, which in this case it's not, then that would be our hypotenuse there, which I've drawn really, really badly, okay? So that would be our third side of the triangle there for the two vectors that we've got. And of course, if you look at that squiggly white line, which I've badly hand-drawn in, it is exactly the same structure, same length, same angle, same magnitude as the resultant force vector. So if we were to calculate that line, it would be the same as the resultant force. In other words, we could, if this was a right angle triangle, we could apply Pythagoras' theorem to actually calculate the resultant force. And that's why this model works. That's why this parallelogram structure actually works. So if you want to go further with that, I encourage you to revisit your Pythagoras theorem, and it will become a lot clearer why this parallelogram rule actually operates in this way. Okay, now, one of the things we have to get our students to do is to be able to write about this thing. They have to be able to draw it too, but they have to be able to write about it as well. I'm just going to take a moment just to sip my drink, and I'll be straight back to do that. Okay, good. So let's start to address how we'd go about actually writing about this thing. So let us remind ourselves that when we describe something, we are looking for characteristics. We are looking for details. We are looking for composition. Okay, characteristics, details, and composition. That's what describing something means, that we give information about those things. So the first piece of advice that I give to you and give to your students, and I encourage you to encourage your students with, is that if a student's asked to describe this and the question doesn't specifically ask them to draw, for goodness sake, draw anyway. Okay, because it is an excellent way of getting the details of the composition and the characteristics. So even if the question does not ask for a draw or an illustrate, it's describing the flight path of a shot put, the student should include an illustration of vector drawing within that answer. And I would go further than that. You know, if we're working with students on, I don't know, energy systems, for example, if we're working with students on anything on the biomechanics side at all, and a drawing is relevant for the answer, but it's not asked for in the question. Draw anyway, okay, and include your description along with it. Now, beyond that drawing skill, which I think would really help here, we need to think about the characteristics and the details that would be descriptive here. We're not saying why at this point. That's going to come in a few moments' time. We're not saying why. What we're saying here is what. So, what are the details of this? So first of all, we want to be making key points. We want to be saying about the release height, okay? Release landing height, okay? So we would be at, as we've said already, less than 45 degrees, okay? So we would put our description in there. Secondly, we're going to be describing the flight of this object in relation to these things. We're going to be saying that it's slow, or we say low velocity. We're going to say that it's got a low cross-sectional area. We're going to be saying that its surface characteristics are smooth or relatively smooth. Okay, so that is, of course, going to limit the air resistance. And the other point we want to be making is that this object is a heavy object, and we could be specific. What do we say? I think it's 7.5 kilos is the heaviest shot, Olympic shot for men. So it's a heavy object. Okay, and we know already that it's a slow-moving object. So as a result of that, we could describe that weight is dominant. Okay, so we could describe that weight is the dominant force. Can we see that in our illustration? Well, the weight force is clearly greater than the air resistance, so the weight force is dominant. We could say that the air resistance is small, and we'll say why in a moment, because we can explain that. The air resistance is small. And as a result of that, the resultant force, the R, is close to the weight force. So if you see here, the R, the resultant force, is relatively close to the weight force in comparison to the air resistance. And that's because, as we said a moment ago, the weight force is dominant, okay? So we can then talk about the flight path. The flight path is what we'd call symmetrical, or at least I try to draw it that way. I'll come back to that point in a second. It's a symmetrical flight path. So we can call it a parabolic flight path. So a parabola, which I'll write down here for you, a parabola is a perfect arc. So if I had managed to hand draw, and I'll more of this point in a second, a perfect arc, this would be a parabolic flight, and it's parabolic, it's symmetrical. Why? Because the object is heavy and it's not moving at high speeds. Therefore, the air resistance is low. So we've got a symmetrical or a parabolic flight path. And my last point that I'd really be trying to get out of students here is what I talked to you about in the last session. So as a result of that, the law of conservation of momentum applies. Okay, remember that law we talked about last time? So we're saying that basically the second that this shot leaves, leaves the hand at this point, this landing place is absolutely predetermined. Okay, we're not going to say why at this point because we're just describing, but we're saying here that the conservation of momentum applies and the landing point is going to be predetermined at the point of takeoff. Okay, so now we've got to come into an explaining skill. So with with explaining, we're tending to be saying why, question mark I should put there, we're tending to be saying how. So how would we go about sort of saying why here? And of course we're going to be saying lots of because type statements, because, therefore, this means. Okay, and you might want to think about our roadmap service, which helps students with that exact skill. So why is this? Well, again, some of our points here apply once more. So this time we're getting symmetry. We're getting symmetry because we often use this orange for our. We're getting symmetry, so we're getting this point here, symmetry because weight force is dominant. That is a relationship between those 2 points. Okay, symmetry because the weight force is dominant. So we've got this notion here. Why? Because the weight force is dominant. Weight is dominant. Weight is dominant. We can put, maybe I should put this point first, because weight force is dominant because the object is heavy and slow moving. And you can also, of course, make the point about the cross-sectional area that we've got over here and the smooth surface, which also limits the air resistance. So we'll make that point. We'll make that point now. So air resistance not dominant, because you don't always have to use because. There are, of course, alternatives. I'm just trying to make it obvious that I'm explaining. Air resistance is not dominant. Is not dominant because it's slow, smooth, and let's just call it relatively small. Please do use the term low or limited frontal cross-sectional area. Okay, that's a much better term to use. So in this case, we are explaining the process. Okay, so now we're going to say therefore, flight is predetermined at takeoff. So no other force is going to influence this object except the pushing force and the release force. So we've got these points nicely made now. They're explanatory, they're descriptive. Now, the only other thing, and I haven't really left myself any space to do it, but the only other thing I'd say here is explain how the performer could improve their performance. So how would we go about explaining that? Well, I guess the first thing to say is release the object at a higher point, so it travels further, so we get a greater release height, so we could have greater release height. So, try and push up higher, and you'll see that athletes do try and do that. Greater release height. We, of course, want more force, and we know why, because of Newton's second law, force is proportionate to acceleration, or the acceleration is proportionate to the force, and make sure you get the angle of release correct, angle of release. Okay, so if the athlete can get those three things as optimized as possible, increased release height, greater force, and training is going to be a good way of doing that, but so is technique and timing, and the angle of release is going to be optimal, and we already know that the angle of release should be a little less than 45 degrees. And if we can get those concepts into our answer in an explanatory structure, we are going to be absolutely magnificent at writing about these things. Okay. Last thing before I move this on quite a long way further, actually, is that we've got a little activity here, and it's just a bit of fun, really, to try with your students. It's got here flight paths. Try this activity to see how height of release affects the landing point of a parabolic flight path. Can you draw a perfectly symmetrical flight path for this shot put? You saw it's kind of hard for me. Starting at the point of release, that's here, going through the center of mass, and the shot put finishing at a landing point where you think the shot put would land. So you're probably going to find that the student says, right, here's my landing point here, for example. You can use pins, mirrors, or anything else to help you. However, you must not use a protractor or an angle measurer. So basically what you're going to say to your students, and you're trying to drill into them the idea of parabolas and parabolic flight. How can the student use whatever resources they've got available? How can they use them to get a perfect parabola? And you will be amazed at the you'll be stunned at the creativity the students come up with, because they really like this activity, and they're going to find numerous ways to make perfect arcs. It's a stunning thing to actually stand back and watch them do this. And now, are they going to get that question on their exam? No. But when they do this question, and they're doing this in relation to a shot, and of course you can still get them to draw the vectors on here as well. There's nothing wrong with that, get them to do that as well. But once they're doing this, are they ever going to forget that notion of a parabola? Are they going to intuitively grasp the idea of symmetry? Are they going to intuitively grasp that a heavy object will have a large weight force and relatively low air resistance force? The answer to those things is yes. So let them spend 10-15 minutes on this and really sort of nail that activity. We've got a final question here. What is another name for a symmetrical flight path? And of course, we'll be wanting the student to put in here parabolic. Okay, parabolic. So they're really nice activities, simple, creative, that get the intuition of that notion going. All right, let me just pause because I'm going to go into some kind of coughing fit. Hang on. I actually, excuse me, still going. I actually should have said a moment ago, if you're working with the AQA exam board on the A level for the biomechanics, you're probably looking at what we've just done in terms of the flight path of the shot. And it probably looks a little bit different to the AQA guidance. What I'm going to do on that one, because AQA do encourage us to teach it completely incorrectly, what I'll do is I'll provide you a specific guidance video for you guys who are interested in that, for how we teach that on the AQA one. But let me be, can I please encourage colleagues that if you are working with the AQA exam board, when you speak to them, you go to their meetings, go to their training, whatever, for goodness sake, encourage them, please ask them if they can reflect on the model in which they use for their vector illustrations, and they really need to change it because it's outright wrong. Anyway, that's another point. But just in case you're worried about that, I'll provide that resource for you. Okay, I think someone might have mentioned that in the chat. So yeah, that's what we'll do. We'll provide you that, but be reassured that this methodology we're using here is absolutely correct. All right, a different example this time. Obviously, this time we're looking at the flight path of a shuttlecock, and what a shuttlecock as well, because the one we've got here is absolutely huge in comparison to the person that's hit it. Anyway, so what we've got here is that this person has struck the shuttlecock. Maybe the release height is something like here. The shuttlecock has traveled like this. Now look at that flight path, which I've just badly drawn in there. We've got a completely different shape flight path immediately. Now I would ask you, can you immediately label that flight? Could you tell me how you would describe that? Okay, badly drawn by me, flight path. And what would we call that? And what I'd be hoping you'd be writing in the chat or shouting at your screen or whatever is that this is what we'd call a non-parabolic flight, or an asymmetrical flight. Non-parabolic flight. Why? Because we've effectively got a shortened flight path. We've got a shortened flight path. Okay, let's see if we can address why that actually is. And it's probably, you know, if you've ever hit a shuttlecock hard, which I'm sure the vast majority of you have, you probably find in this case that yes, in this case, you know, we do find that the shuttle does travel in a non-symmetrical path. So can we vector illustrate that concept? Let's always remember we've gone in this direction this time. Let's always remember that we put our direction of movement arrow in. So just a scruffy old direction of movement arrow for me, because I'm not going to waste any time in it. What colours did I use for air resistance? And so I had green and yellow. So let's stick with the same things. So first of all, this time I'm going to get my ruler. I'm going to try and get it to 90 degrees, which with this little pen is kind of a little bit complex. And we're going to put here a weight force in. Now, the centre of mass of this object is in the centre of the cork. The feathers weigh almost nothing, bit of glue, bit of wood, but the weight of this object is in the cork, which is ultimately why it flies the way it does. So we're going to go from the middle of the cork down, and the weight force in this case is going to be minuscule. So there's our weight force. I mean, it's almost not there, right? There's our weight force. I'll label it just there. There's our weight force. Tiny, 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 tiny weight force. Because why? This object's light. Now, a little bit of guidance on the shuttlecock. The weight force should go to approximately the outer edge of the cork itself. So that's approximately how long you want it to be. As long as it's shorter than the air resistance, that's the important thing. Now then, we now want to put the air resistance in. So let me turn this little object around. We've got that there. Now, our air resistance is going to be back along the flight path. So approximately we're at that angle now. So now my air resistance, I think I've used the resultant force coloured pink by mistake here, but never mind. So now we've got an air resistance which is really, really long. Okay, so now there's our air resistance. And my attempt with the angle here, my attempt with the angle is that it was going back along the flight. So just to be clear, if we had the shuttlecock here, which we haven't, but if we had the shuttlecock here, we'd actually have air resistance going in that direction this time, but much shorter. Okay, so just it goes back along the flight path. That's what I'm trying to say there anyway. Then how do we get to a resultant force? Well, of course, what do we do here? Well, we use our parallelogram. So our parallelogram this time, I'm going to use the pink again just to make it clear that I'm drawing a parallelogram. So we have our pink parallel line, which is going to be a bit like that. I think I went too far. And then I'm going to rotate to 90 degrees. Where are you? Oh, that's hard to do. And then we're going to have our little green line our little green dotted line like that. So now I've got my parallelogram, and I've used the wrong colours altogether, but now I can draw in my resultant force, and I've got that pretty accurate, not too bad. So something like that. I'm going to rush this a little bit. So now I've got my resultant force, okay? So my resultant force. So get rid of this. So now I've got my resultant force, which is over there, R, resultant force. And already we can see a substantial difference between how the appearance of that vector illustration of a projectile and this one. We've got the same methodology, but while this one, the resultant force is almost vertically down, on this one, the resultant force is almost horizontally right. So we have a completely different notion of flight in this case. So a couple of things we want to say first of all. For a couple of things, we want to say that R is close to air resistance. Okay, so if resultant force is close to air resistance, what this means is we get rapid deceleration. And that should hopefully be intuitively kind of obvious for you if you think about the experiences of hitting a shuttlecock hard. Okay, so you get rapid deceleration. And as a result of this, we get a non-parabolic flight. Non-parabolic flight. And we get what we call a shortened flight. A shortened flight. Okay, so we've got this completely different notion. We've got a completely different arc. Well, it's not an arc. We've got a completely different shape of a flight. And the reason that is because the air resistance is dominant. The air resistance is dominant. And when we've got dominant air resistance, resultant force will be close to the air resistance. We'll get rapid deceleration, and the flight path will not be parabolic. So, of course, in many situations, you might think, well, we want to limit air resistance. And sometimes that is the case, you know, if we're trying to move something fast. But there's also beauty in this reality because, of course, this person here can hit the shuttlecock really hard, and she can be, assuming she doesn't hit it too hard, she can be relatively confident that it's still going to land in at the back of the court. I mean, think about all of the 13 and 14-year-olds you've ever done badminton lessons with. How many of them could hit it from the back of one court and get it out at the back of the other side of the court? It's a hard thing to do for a child, right? I mean, it's a hard thing to do for an adult unless the technique's really good. So this structure gives meaning to that game of badminton. Okay, so badminton in many ways is absolutely defined by the nature of this flight. I'm going to say that again. Badminton in many ways is defined by the nature of this flight. So I guess this particular shot would be some kind of clear shot, right? This would be some kind of clear shot, right? Because of course, if they were doing a smash shot, then the flight would be a different kind of thing altogether. It would be sort of a downward trajectory. So this trajectory is upwards, so it's a kind of a clear shot. So look, we've got the same notions here. How would we write about this? I'm probably only going to give a couple of examples here. So we would have the same point here, release and landing. We'd have less than 45 degrees because, again, the release height is actually, again, above the landing height. This time we've got a different situation. We've got a very fast shuttlecock, and the cross-sectional area is actually relatively broad because if you think about the object, okay, it's got a small nose on that cork, but then the shuttle actually kind of spreads out in that direction, right? So it's actually a relatively broad object. Okay, I know you're going to say to me, well, the shot's narrow, but it's all relative, like, to its weight. And we're going to say as well, is the object smooth? No, it's a rough surface. So it's a rough surface. You know, you've got lumps of glue, wood, everything all over this thing. So it's catching the air as it flies. Going back to what we said before, it's very light. The air resistance is dominant, the weight is small, so therefore resultant is close to the air resistance, it's asymmetrical, non-parabolic, and it doesn't fly according to the laws of conservation of momentum. Its momentum changes. And again, we could go on to this side here. It's asymmetrical because air resistance force is dominant. Air resistance is dominant because the object is light and fast. Air resistance, we'd put here weight force, not dominant because it's light. We could also say air resistance is dominant because it's fast, it's rough, and it's got a large relative cross-sectional area, and therefore the flight path is not predetermined at takeoff. It's determined by the air resistance. So we could put all of those points, and I encourage you to do it. I'm just not going to sort of spend sort of 10 minutes now going over those same points with you. I'd encourage you to put them in, but we want a full description and explanation of that. And let me remind you, it's important that the students also grasp the idea of how they're going to draw that in their exam if they get that question, or if they need to represent those ideas, they need to be able to draw those things. Now then, let's move this on, and I'm only going to look at this briefly, because what we could do here is we could look this by the way, believe it or not, is a javelin. Okay, this by the way is a javelin. Okay, so I'm just gonna offer you some thoughts on this, and then I'm going to explain it a little bit when we change canvases, or at least I think I am. So what I'm going to do here is the javelin again. We have a projectile again here. Okay. We basically, projectiles, anything that fly through the air. Sometimes, by the way, we also consider someone on ice to be a projectile, because the ground reaction, the friction is so small that we consider it to be effectively in flight. Anyway, that's another point. With this, let's draw on our primary information. Okay, so how would we go about doing this? We take the center of mass of the javelin, which is going to be towards the tip. We take the center of mass of the javelin, and we're going to draw onto that center of mass a weight force. So it's got some weight to it. It's not a particularly heavy object, but it's got some weight. So we've got a weight force. Okay, so we know that. Okay, so we've got our weight force. We've got, what am I doing? We've got, we've got some air resistance, whose colours are, let me try something different. We've got an air resistance because it's travelling. It's not travelling especially fast, but it's a little bit faster than the shot. So we've got some air resistance. Okay, so there's our air resistance. Okay, so I can put my label there, air resistance. Now you might think, well, James, now we can do a parallelogram of forces, and we could do a parallelogram which was kind of something like this, right? We could do something like this, draw the result, and boom, done. But I want you to think about something. I should have said direction of movement, of course. Hope you picked me up on that. But in this example, and this is where we're going to go with these ideas, we have something additional. And all I'm going to do here is I'm going to just introduce it to you. We have a third force acting on this javelin during its flight. Not when it's in the hand, not when the action force is being applied to it, during flight. And I encourage you to try and think coherently, clearly, imaginatively if necessary, what that additional force would be. I'm going to draw it on for you, and then we're going to come back to it both in this session and in the next session. So here we have, I'll use a yellow. Here we have our additional force. And I'm going to draw it like that. And for now, all I'm going to label it is L. Okay, and the thing I'd encourage you about now is what is going to happen in this example. How would we bring about these resultant forces? Because we've got a weight force, we've got a air resistance force, and we've got this mysterious L. First of all, what is L? What is L? And secondly, how do we generate, or how do we illustrate resultant force? And let me reassure you that we have gone through all of the skills so far in this course that would allow you to illustrate the resultant force of this object. So I would ask you to consider how that would work in this example as I change the canvas. So I'm going to be a couple of moments just changing the canvas. If you want to put some thoughts into the chat, we'd be really keen to read them and see what you have to say. If not, don't worry, we can go from there. But how would we go about doing that? Just change the canvas straight back. So I've been given the hurry up here a little bit from those that are around me. Thank you so much for the pressure applied. So yeah, I think we're going to be a little bit tight for time. We'll hopefully finish on the hour as normal, but it might be 5 past. Just be aware. Okay, let's move this on. I've been asked the question here: using a sporting example, describe the law of conservation of momentum. Can I just remind you as well that all the questions we demonstrate in these sessions, you're going to get a full copy of all of the questions with all of the model answers, so you can use them. You'll get the paper, you'll get the mark scheme, and you'll get the model answers. Okay, so they will come to you at the end of the 6-week block, so you can use those at that point. So be reassured you'll have those. So anything we show. So using a sporting example. Describe, there's my skill, the law of conservation of momentum. So again, I'm looking to give details, I'm looking to give characteristics, I'm looking to give composition, characteristics. In this case, I'm going to be saying is characterized by, in this case, I'm going to be saying the law states that. But this is what I'm trying to get at with any kind of description, the details of it, the characteristics of it, and the composition of it, of course, with relevant, correct material. So what I've done is I've actually got an answer in advance. Let's just go over it. The law of conservation of momentum states, here's my key skill, I'm effectively defining at this point, that the flight of the jumper, okay, let's actually, let's make our answer better. Let's actually make our jumper bear with me a second. Let's actually make our jumper a long jumper. I think that was rather than just a jumper. So the flight of the long jumper will be predetermined at takeoff. So there's our circle, tick, and 1 mark for saying what the law is. The centre of mass will travel in a perfect arc. We call this parabolic. I actually think that would get a mark as well, because the weight force is dominant. So again, how would the examiner mark this? The predetermined, circle, tick, 1 mark. There's going to be some reference over here. Let's say that was 0.3 on the mark scheme. Weight force is dominant, circle, tick, 1 mark. Maybe that was 0.5 on the mark scheme, who knows. And the jumper cannot change the flight path of the centre of mass, which is true. They can change the position of the centre of mass, or they can distribute their mass around that centre of mass, but they can't change the flight path of the centre of mass. The horizontal distance travelled by the centre of mass is predetermined. Circle, tick, 1 mark, and then we're going to be into our max in that situation. But we've got a bit more. All the performer can do is to manipulate their body around the centre of mass by pushing their arms and legs forward at landing, so the feet strike the sand in front further than the landing of the centre of mass. Okay, so what we're saying here is that, okay, the flight path of the centre of mass, so here's our takeoff board, here's all the sand over here. So what we're going to say here is that the centre of mass is going to travel in a perfect arc and land here. But what the athlete is going to do is they're going to try and get their feet to strike the sand here because it's further. And that's what that last point means. But we have clearly described the law of conservation of momentum. So once an object, a heavier object, is a projectile, no other forces are going to act on that, and the weight force is going to be dominant, meaning a parabolic or symmetrical flight path. Different skill here. I'm pretty confident you could have a really good go at this, but we've got here, the image below shows the flight path of a shot put and a shuttlecock. Compare the flight path. Not sure why we're not doing so well with our grammar today, or with our capitalization in this case. Compare the flight path of the two objects and explain why they have different flight paths. So we've got to compare and we've got to explain. So first of all, let's put the answer in. And again, I'm pretty confident from what we've done today, you'll be able to have a good go at this, but let's actually look at what the construct of the answer would be. The flight path of the shot put is parabolic. Okay, so we've got the shot put here, the green path, which is parabolic. Okay, whether that's the right angle is another matter. Symmetrical. Comma space, whereas the flight path of the shuttlecock is non-parabolic. Can you just first of all take that first, that first sentence there, actually ends here, look. Can you realise for me that that is clearly comparative? Okay, because we have taken two features, one of each of the shot and the shuttle, and we've compared them. The shot is symmetrical, parabolic, comma space, whereas, look at that structure, comma space, whereas the shuttlecock is non-parabolic. We are clearly comparing. The dominant force of the shuttlecock is the air resistance, full stop. In contrast, comma, the comma is important. The dominant force of the shot is weight force. So again, comparative. The resultant net force of the shuttle is closer to the air resistance. Full stop. However, comma, must be there, the resultant force of the shot is closer to the weight. So we've now got three comparative statements which are accurate, picking us up potentially 3 of our marks. Finally, the flight of the shuttle is shortened, comma space, whereas the flight of the shot is in a true arc. We make our 4th comparative statement. Now, I would argue here that we should go on to explain, okay? But I want to, as we've kind of already done that, we could explain why for each of those points. But as we've already done that in the session, I'll kind of leave you to add that detail. We would, I mean, that's a beautiful comparative answer. Beautiful, because every statement is comparative and every statement must be comparative. If we're asked to compare and we don't compare, we shouldn't get any marks for describing. I want to be really clear on that. In my opinion, can't speak for any exam board, in my opinion, if a student is asked to compare something in an exam question and they just describe 2 different things, in my opinion, that is a 0 mark answer. It should be comparative. Their statements have to be comparative. And the students deserve that we develop that skill with them, because it's a very essential life skill as well. Anyway, I'm going to stop banging on about that. But we've got some nice answers there. We're clearly performing the skills that we're required to perform. Now then, last thing for today, and I'm probably going to do the first part of this, I want to introduce you to the notion of fluid dynamics. Now, be aware that with fluids, we are talking about 2 things. We are talking about liquids and we are talking about gases. Okay, so we're talking about the dynamics of how things move in liquids and gases. So, of course, for us, we're particularly interested in how sporting objects move in water and how they move through the air. Okay, so that's the liquid. They're the liquids and gases we're interested in. And I initially want to introduce you, probably the only thing I'm going to do now, to what we call Bernoulli's principle, which is going to lead us nicely into session 5 next week. And Bernoulli established a very interesting experiment, and it might help you to think back to that javelin example I raised a moment ago and questioned you about. But it didn't quite look like this, but what Bernoulli did was as follows. He got a fan. Here's my fan. My fan has, I don't know, it's got some blades that blow air, and it's got legs. I'm going to imagine, you know that classic fan we've all got. I'm going to imagine I've got a fan like this, like that fan you have in your living room in the summer that you quickly go out and rush to buy because there's a heat wave on or something. And basically, these fans, industrial fans, they were blowing air into a vestibule or a space like this. Okay. And what Bernoulli did, bless him, was he put sensors here, here, and here. So these little things, this is going somewhere, don't worry. These little things are sensors, and they're sensors of pressure. In this case, air pressure. Okay, so they measure what air pressure the air is at in that particular point. Okay, so of course this air is blown in here and the air travels in this way. And okay, the air is moving at this point for, let's call it sensor number 1. So there's number 1. So sensor number 1, the air is moving. But as you can see here, the air is in quite kind of a wide chamber. Now I want you to think about what happens to the air speed as the air enters this point. Okay, and what of course we find is that at this point, and at sensor number 2, the air is traveling faster. Now remember, the sensor is not measuring the air speed. The sensor is measuring the air pressure. I'm simply saying that at this point, the air is faster. Why? Because it's been squeezed through a narrow space. And of course, as the air comes back out into this opening, this other vestibule, to sensor 3, here, we've effectively got slower air. Okay, slower air. So we've got slower at point 1 and point 3, at sensor 1 and sensor 3, and we've got faster at sensors 2. Hopefully that kind of makes some kind of intuitive sense to you. If you're thinking, why is it going faster and slower? It's related to the amount of space, the air, which of course is being pushed through a standard force. It's the amount of space the air has. Of course, it accelerates in this narrow space because there's more mass trying to get through a smaller space. So what Bernoulli found was as follows, was that slow-moving fluids, air and water, let's say, slow-moving, have high pressure. Whereas fast-moving fluids, let's think air for now, have low pressure. So I'd like you to look back at my little illustration here, and where is the pressure high and where is the pressure low. And hopefully what you're going to be saying is, well, the air is slow here, so here we have got low pressure. So, do you see how this can be confusing? I hope you were thinking, James, what are you saying? So we've got here, I apologise, slow moving air, so we have high pressure. Here we have fast moving air, so we have low pressure. Here we have slow moving air again, so of course we have high pressure. Now you might be thinking, James, why on earth are you talking about this? Well, it is for this reason that our example from earlier, I'm just going to sketch it in, which suggested we've got direction of movement in this angle for now. We've got our weight force. We had our, I can't remember what colours I used, so forgive me. We had our air resistance force, and if you remember, we also had a third force, which was L. And all I'm going to leave you with for now, because we're going to look at this right at the start of the next session, all I'm going to leave you with for now is that this idea and this L is achieved because of exactly this Bernoulli principle, exactly this reason. So what I'd like you to do is kind of in some kind of discovery mode, I'm sure many of you already know it, I'd like you to think about how then that concept we've just addressed there influences this flight. And we're going to talk next time about the notion of an angle of attack. And of course, we're going to talk about what we refer to, and you probably already know this, that the L is a lift force or a Bernoulli force. And we're also going to have a look at the notion of downforce. Okay, so that's going to be at least a big chunk of what we do next time. We're also going to look at spinning objects through the air as well. Right, so I'm going to go back into the camera so we can take some questions and we can answer some things that people want to know. Feel free to ask about this if you're interested, but otherwise we'll move on. Cheers.
Okay, so let me get my water out of the way for a second. Good stuff. So some interesting stuff there, I think. So yeah, just opening up for questions. In fact, before we do questions, I don't know how many we've got, but before we do the questions, just one thing there. We actually had a really poor bit rate tonight on the what's called the upstream. We're actually not sure why that's happened, but hopefully it hasn't interfered with your viewing of that at all, because it hasn't affected our end in terms of the stream coming through or getting there, but it just wasn't quite where we've been used to having it in any of the shows we've done recently. So not totally sure why, but if you had any kind of pixelation, that might have been why. Hopefully it hasn't been, but yeah, we're not sure. So yeah, Marta.
Hello.
Hi. Any questions that you'd like to go over?
Yes, we've been asked, one thing we've been asked a couple of times is whether you would apply what you've explained to any other projectiles other than the shot and the shuttlecock, whether you would apply to anything else.
Okay, so it depends on the course that the students are studying. In the A-level courses, with, if I think, trying to think clearly, the ones with the AQA course, no. With the OCR course, potentially they could be asked something like a long jumper. Okay, a long jumper would be the one to do. And the long jumper would be almost identical model to the shot put. The only thing is a long jumper moves through the air slightly faster than a shot, and they're a little bit heavier. So the ratio of air resistance to weight is the same, but you might just want to adjust the vector length a little bit. But that's the only one. The only other one I'd say is close to it, and we looked at this last time, is the example of the action force and the weight force on the golf ball as it's being struck, but that's not a project at that point. So that's a different one.
Mm-hmm. Thank you.
Any others?
No. Well, personally,
Mm-hmm.
I would like you to explain again, if possible, the Bernoulli principle. I struggle a little bit with that, and I could do with a little bit.
Well,
Yeah,
can
a
you
bit more
first of all, Marta? I was intrigued by your pronunciation of his name. Would you like to give us a little demo of what you think it should be pronounced?
No, I won't. No, I was wondering if it was more Bernoulli, like Italian, but seems to be Dutch, so I will refrain.
Okay, so let me go on to Bernoulli principle. The key takeaway, and when I first learned it, it's kind of counterintuitive, or at least it was to me. The key takeaway is that if we have an object, let's say I have my phone here next to me. If we have my phone, if my phone is kind of flying through the air, if there's a different air pressure underneath to that which is on top, that air, by its nature of it being a fluid, has to actually correct the differential between the air pressure. So on that basis, if there's fast moving air on one side of, for example, a ball or a javelin, and there's slow moving air on the other side of the ball or the javelin, then there's a pressure differential, and then we're going to effectively get a force acting as the pressure attempts to equalize itself. And I can actually demonstrate that. So I'd encourage you to try this at home. Some of you will have done this. Some of you will have done this before, I'm sure. But if you get a bit of paper, this is just roughly a bit of paper. What I'm going to do here is I'm going to put my top lip on the paper, and I'm going to blow so that my breath goes across the paper this way. So the top's going to have fast moving, lower pressure air according to Bernoulli. And the bottom is going to have stationary air or slow moving air and higher pressure. So according to that theory, then, if we've got high pressure below, low pressure above, this, when I blow across it, should lift up, theoretically. So let's see if I can make it work. Oh dear. So you see that lifting effect of that. Another great way of demonstrating that, or a great way I've used it in the past, is if you get something like a snooker cue or a piece of wood, and you hang two balloons from it on a piece of string, so that there's two balloons here and there's a gap in the middle, and then you fire a fan's air in between the two balloons. What your intuition will tell you is that the balloons will separate and move away. But in fact, what the balloons do is they come together and hit each other in the middle, and that's because there's faster moving, low pressure air in the middle, and slower moving, higher pressure air on the outside of the balloons, so that pushes the balloons in. And we'll have a look in the next session about why that, actually, or how that affects projectiles. I'm just looking on the live feed of the chat. We've got a question here from Alice. For the flight paths activity, is the question the whole explanation, or is there further guidance for teachers in the resource pack? So for the flight paths activity, I'm assuming you mean the one with the shot put and the symmetrical flight. We don't really have an explanation for that because there's so many different ways to do that. But the way you'll probably find is what you're going to find, or what we see a lot with the students do, is they manage to get kind of quite an accurate arc on one side because there's only a small difference between the release point and the center of mass, and then they use the mirror to try and mirror that out on the other side. Or sometimes what you get is the students try and place pins along an arc, then they put string along each pin, and then they draw their pen along the arc. And of course the string by its nature will arc in a natural format like that. So it kind of works. It works quite nicely. But there's about a million different ways to actually do that. So there's not a specific one. So Tim Brown, James, if the air is squeezed, why is the pressure low? Oh, the sound has just gone. I think we're okay for sound. Yeah. Tim said the sound's back. So if the air is squeezed, why is the pressure low? So the thing to think about with Bernoulli's principle is not the space that the air's got, but it's simply the relationship between the velocity of the air and the pressure of the air. And that's why, for me, when I first learned that, it was counterintuitive, because it was like, well, it's kind of in a tighter space, so there should be more pressure. But no, there's the same amount of matter, but of course it's being pushed through at a faster rate. And what Bernoulli told us, or what his research showed, and for me it's a really counterintuitive concept, is that as soon as air is moving faster, the pressure of that air reduces. So that's really the takeaway to grasp. That you will find with your students that sometimes they won't like that to begin with, which is why those little experiments like the paper one, the balloons, is a good idea, because it proves that point. Although I read something on a line the other day that said that there were actually other factors at play, but I'm not going to get into that. So Lindsay Taverner, could you please repeat the explanation of why the lift acts upwards in the paper, e.g. Okay, let me do that again, Lindsay. Okay, so when I blow across this in a moment, my breath, beautiful and rose scented, obviously, not like a guy who's had 6 cups of coffee and worked too hard in a day and is still working now. What's happening is that air is moving fast across the upper surface of the paper. So above the paper, the air is going to be moving fast. Below the paper, the air is going to be stationary. So the fast moving air above is going to be low pressure. The stationary air underneath is going to have higher pressure. So there's going to be high pressure here, low pressure here, and it's going to lift that paper up. So if I try that again, let me just move this out of the way. You can also try it. It wouldn't be easy for me to do this now. You can also get 2 bits of paper, put them on, you can sort of put them on your desk like that, blow down the middle of it, and it'll bring them together rather than forcing them apart. It's the same principle. So the air in the passageway is moving fast, or faster than the air outside of the paper, and therefore you've got a pressure differential. As soon as you've got a pressure differential, you're going to have an equalization of pressure, because that's what fluids do. So yeah, hopefully that answers that a little bit. So other questions, Marta, anything you want to move on to? Before we finish, we do have a couple of special guests in the audience that I don't know if you know, Marta, but your sister's tuning in at the moment from San Lorenzo Dons. I don't know if there's anything you want to say before we finish.
Hola.
So,
Hola,
sí. Hola, Gisela. ¿Qué tal? Y gracias. So yeah, nice to have them here and sort of supporting what we do. We'll be back to you guys this time next week when we've got our session on airflow, and we're going to do really look at the Bernoulli principle and the Magnus effect, and that's some really fruity, gritty stuff in biomechanics that we're going to get stuck into. You've already got the basic underpinnings of that already. We're also going to look as well how a cricket ball deviates in its flight. It's all based on the same principle, and then that's going to leave us some really cool stuff in the last session where we look at planes, axes. We're going to look at the principle of moments, and we're going to have a look at angular momentum in that 6th session. So yeah, really looking forward to it. Really enjoying myself. So yeah, what are you laughing at, Marta?
Oh, no,
just giggle. It's
fascinating. Yeah.
Yeah, really, genuinely
It is
fascinating.
genuinely fascinating.
Yeah.
Yes.
I'm not sure your sincerity is coming through as you believe it is. So anyway, I'm gonna say goodnight. All the best, folks. Thank you so much for giving up your time as always on a Thursday. This show will go straight on to Tuesday. What am I saying? A Thursday. On a Tuesday, and this show will go automatically into the on-demand course. It should be in there about middle of tomorrow by the time we get it in there. So yeah, lovely. Happy to be here, and yeah, all the best. See you soon, folks. Take care.
Have a good evening. Bye.
Cheers, guys.